Thank you, Dalcott, for this introduction. Thank you, the organizers of this meeting, for inviting me. Yesterday, Anne Goujon's, she said, religion is hot, sex is hot. This is much hotter. I will start by first justifying why we need probabilistic forecasts. Not only population forecasts, but any forecast in social science. It is to improve decision making. Then I will use a few words on the methods, how we produce these forecasts, and in particular I will show you what Wolfgang's contribution has been in the field. And then I end by something that I noticed as a surprise: scenarios and education. They came as a surprise, at least in Wolfgang's recent work. Yeah, this works. Can you hear me when I'm talking like this? No? Okay. Right. Probabilistic forecasts. Probabilistic forecasts are a big aid in decision making. The Norwegian Parliament has decided to buy 52 Joint Strike Fighters. And since the price of these fighters, these airplanes, is unknown, they are still in the construction, the price is a forecast. So the Parliament asked the Lockheed company, how much will it cost? And they came up with a price estimate of 61.2 billion for 52 airplanes. That was a median forecast. That's what the Parliament wanted to have. In addition, they wanted to have a forecast that would be cut with 85% chance, and that's a bit higher, 72 billion. Now the difference between these two tells us something about the range of uncertainty. And on the basis of that and other big projects, the Norwegian Parliament can take a well-informed decision. Planners, in order to make good decisions, they need this kind of probabilistic forecast. Because the deterministic forecast with scenarios or with variance, they leave room for political decisions. The Clinton government was shut down. The Clinton government had a quarrel with the Republicans in 1995. And since there was no budget, the government had to shut down for a short period. What was the case? Well, the Clinton administration had prepared a budget forecast which was much more optimistic than another one which was pessimistic, which showed a deficit. And the Republicans didn't want to accept that. So they were quarreling quite some time. They used two different forecasts, two different deterministic forecasts, politically decisions here. And that is not a good practice. Now to population forecasts. We are used to high, medium and low variance for births, for deaths, for migrations, for fertility, mortality, migration. The common opinion is that there are logical flaws when interpreted as uncertainty variance. You cannot do that. For instance, the prediction interval, the gap between high and low number of births and the gap between high and low number of deaths doesn't necessarily have the same probability coverage. Inconsistent. Also, when you have derived variables, for instance, the difference between birth and death, natural growth, and you compute the probability that the interval will be somewhere between a high and a low value, then the probability will be very different than the assumed probability for the high-low interval for the two components, birth and death. It's inconsistent to treat the high-low variance as uncertainty variance. They do not reflect uncertainty. So I very much liked the statement that I found in one of the writings of Wolfgang and Sergey, a probabilistic projection clearly gives more useful information than the usual high and low variance. And I assume this was written in 1998, that you still have the same opinion. At least I support it fully. Now, deterministic forecast, cohort component approach. We know that since 1895, Edward Kennan, who developed it, it was implemented as a regular method in statistical agencies in the 1930s. And the idea is that you have a vector which breaks down the population by age and sex. Let's say 200 elements when there are 100 age groups. And you adjust this vector forward in time, you adjust it to a later point in time. Just revise it by multiplying it with a matrix of transition probabilities. And the transition probabilities are then functions of underlying rates, fertility rates, mortality rates, out-migration rates, and immigration is treated as an additional factor. Okay? Later on, Andre Rogers and Frans Willekens, they extended this method to multi-state method. Deterministic forecast, fine. Now, a probabilistic forecast goes exactly the same way, except that the transition probability matrix P, as I showed it in the previous slide, now is a matrix in which all the elements have a probability distribution. They're random variables, it's a random matrix. The first literature is from the 1960s and 1970s. Joel Cohen contributed to that, John Pollard, Ture Schwede, Sykes, of whom I do not remember first.
Zeno.
Okay, thank you. Thank you. Yes, yes. And they aimed at obtaining analytical solutions. One major problem there was that there are a multitude of covariances. Men and women are correlated. There is a correlation across ages. There's autocorrelation across time. And to find out proper analytical formulas for the variance of the results, the resulting population factor, and how the uncertainty propagates through the age structure is not a simple thing. So therefore approximations had to be used. It was not until 1985 that Nathan Kiewitz published a paper in Zeitschrift für Bevölkerungswissenschaft in which he used a simulation approach. Very simple simulation from a uniform distribution, but still. Anton Kuijsten, Bevolking en Gezin, used the same method 3 years later. Nowadays, a frequentist approach with a much more flexible model when it comes to probability distributions is one that we call the model for scaled error. Juha Alho of nowadays Helsinki University is the person who constructed it. And also he wrote a very flexible computer program, PEP, propagation of error population. So I have to check. Alzheimer light. Thank you. Program for error propagation. Thank you. Extremely flexible. There are a number of examples of official population forecasts published in the form of probabilistic forecasts, probability distributions. New Zealand and the Netherlands are two examples. You can check that in the links that I have here. A few other countries are experimenting. I mean, the statistical offices are experimenting with the probabilistic forecast. Francesco told me yesterday that Italy is on the verge of publishing a probabilistic population, Istat population forecast. Perhaps there are more countries. One important example is, of course, the United Nations. Adrian Raftery and a colleague from Washington, they have used Bayesian methods to assist the population division in producing probabilistic forecasts for all countries in the world. It's Bayesian thinking, it's state-of-the-art, I think, because the authors that I mentioned so far, but even Juha Alho, have a frequentist approach. Here, there's a Bayesian approach. it is much more flexible. I also mentioned what I call the Southampton School, Jacob Bujak, James Raymer, originally from Southampton, so sorry, at least you contributed a lot, and then the colleagues in Southampton, they apply Bayesian thinking to probabilistic population forecasts. Now, in the second half of the 1990s, Wolfgang, Warren, Sergey, and also Alexander Hanika, they contributed to the development of these probabilistic population forecasts. The earliest paper that I was able to trace was one in Statistische Nachricht in 1997. Okay? An application to Austria, which later was also published in English in the European Journal. There's also one application in the Zeitschrift für Bevölkerungswissenschaft for Germany. And then the revised volume of Future Population of the World, 1996 edition, has one chapter in which there are probabilistic population forecasts for all countries in the world. Later on, Wolfgang and colleagues published also a number of papers in Nature, Science, and in Population Development Review with these probabilistic world population. 13 big continents, groups of countries, first world regions, later on all countries in the world. Here is one famous figure from the early attempts. Doubling of world population is unlikely. And you see it in the graph. There's only 1/3 of a chance, 33% chance of doubling world population, because a population lower than 67% is much more probable than, that lower than a double one is much more likely than one that is exceeding double the population size. These are the kind of fans that have become very popular in probabilistic population forecasting. When I see this green and yellow colors, I immediately think of the Yasa School of Probabilistic Population Forecast. They're typical of the way Sergey and Wolfgang and Warren present their findings. This is one study for Germany, which was part of a European project with probabilistic population forecast. You can't see all the details, but here we see that aging is nearly unavoidable, nearly 100% certain. At least when we look at the lower bound of the prediction interval, then it is such a margin that a share population age 65 and over lower than this one, which would then imply a constant share and no aging, is extremely unlikely. Reality, no doubt, will fall somewhere in between here, and then at least in terms of these prediction intervals, there can be temporary changes, of course, and fluctuations, but the picture that we see here tells us that aging is virtually certain in Germany as it is in many other countries. The main idea that Wolfgang and colleagues had was to ask experts to specify an interval for total fertility rate or life expectancy or net migration number at a certain point in time in the future, a certain calendar year in the future, and then state some probability. For instance, 90%, expert-based. Okay? Now, assuming that there is a certain underlying probability distribution, for example, a normal one, which is much more realistic than Kiefitz's uniform distribution, a normal one, or when it is a variable close to zero, a log normal one, okay, that's a technical thing, then the program draws from this probability distribution in year t, 2030 or 2050, and the program then draws a straight line from jump-off year, 1995, to 2030, a straight line. And that is the reason why, I think it was Tulja and Ron Lee who baptized this as a random slope approach. Okay? There is perfect autocorrelation. It's a straight line, but the slope is is random. Later on, this very strong assumption of a perfect autocorrelation was relaxed by introducing a specific time series model, a moving average with 31 terms in the The advantages of this approach are that it is quite easy to explain, it's easy to apply, it's quite simple. Much simpler than, for example, the Bayesian approach that nowadays has been used in a number of applications. One big disadvantage is that there is very little empirical basis for the covariances that have been applied. And these variances and covariances and correlations, they are important because, as you have shown in one of the chapters by sensitivity analysis, when you assume no correlation between fertility and mortality, or alternatively perfect correlation, for some of the outcome variables, it certainly has a big impact. In my view, you and your team have contributed, have made important contributions to this whole field of probabilistic forecasting. Later on, there were refinements. Francesco, with Rebecca Graziani, have developed, a somewhat more advanced approach by taking into account autocorrelation in a much more systematic way. Then I come to recent work of Wolfgang and the colleagues, and then I was surprised. Why is the future uncertain? Why do we need probabilistic forecasts? Well, there may be two reasons. One is that there's a temporary lack of knowledge. When we work hard enough, scientists, we will fill the gaps. The other one is that human behavior, at least partly, is inherently unpredictable. And probably reality will be somewhere, the truth will be somewhere in between. And therefore, because of one of these two reasons, or both reasons, there are errors in our forecasts. Now, in recent work, and Phil made that point already earlier this meeting, Wolfgang seems to be less occupied by probabilistic forecasts and go back to deterministic ones. Nowadays, he's working on education in multi-state forecasts, deterministic, and he's working on scenarios, both of them deterministic. And that's a bit of a surprise, I think. When we take the point of education, does it completely fill the gap in our existing knowledge so that we can get rid of the probability and we have a perfect causality and we can perfectly predict? Probably not. The causality is rather unclear. Causality between education and components of change, fertility, mortality, migration. Brian already asked the question, is the relationship between education and fertility, is it stable? I would like to go one step further. What do we know about the direction of the causality? Okay, education has an impact on fertility, on mortality, on migration. No doubt about that. But there's also reverse causality. Fertility may have an impact on education. When you're a girl in Bangladesh, you're pregnant, age 18, you cannot attend university or secondary school. When you're dead, you cannot go to school. There must be an impact from mortality to, well, via health, through health of course, on education. And also brain drain. There must be an impact from migration on education. There is, in my view, a much more complicated relationship between education and the three components of change than the one that is assumed routinely in the world population forecast that Wolfgang has been publishing lately. In chapter 2 of the thick book, there is some discussion of this issue, reverse causality, and as Bill Butts reminded us, Wolfgang and colleagues, they talk about functional causality. When is a relationship, when can we talk about functional causality, relationship between two or more variables? Well, there must be a strong empirical association. Okay, that's the same whether we take causality flowing this way or the other way. Right. There must be a plausible narrative about mechanisms. Yep. When you have bad health, you cannot go to school, and therefore, in my view, it's plausible to talk also about reverse causality when we think of mortality and education. Other competing explanations ruled out the dominant factors. What is dominant? I don't know. It's rather vague. So therefore, thank you. In my view, there are competing explanations, not when we think of fertility and primary education, that is convincing, but secondary and later education in the future, which will come to much more dominant, then certainly there is reverse causality of these two factors. And therefore, I don't think that the arguments that you put forward, except two, are very convincing. I would like to see a probabilistic forecast, and in the discussion you mentioned that that is perhaps future work. I would like to see a probabilistic forecast including age and sex and education. Not simple, there are methods, and we would be happy to contribute and assist you. Final point about scenarios. In my view, scenarios are extremely useful as a platform for discussion. When there are many elements, many input factors, they are combined in a very consistent way. You have a narrative, and it seems logical to follow. And the scenario forces you to have a very consistent picture. Alternatively, a scenario can be used as sensitivity analysis. Okay? This is something for modelers, not really for users. Users are less interested in scenarios, in my view, at least when you confine yourself to fertility, mortality, and migration. And that is what Wolfgang and colleagues are doing nowadays. They take some of the scenarios of the YASA SSP set, take out the human factor from them, fertility, mortality, migration, and then include them in the world modeling. So what they then ask the user, a user who wonders which set of projections is more likely, okay, the answer by the demographer is when you have reasons to assume that the assumptions behind the first one are more likely, then you pick that one. When on the other hand you have reasons to assume that factors behind the third one are more likely, then you pick that one. And then the user asks, well, you're the expert, please give me. I mean, in my view, to cover uncertainty, to deal with uncertainty, the scenarios are less useful than probabilistic forecasts. I'll skip. Yeah, final point. I think that scenarios, they answer a question that the user doesn't ask. And the question that the user does ask is not answered by scenarios. And that is, what can we expect? And how probable is that in the future? So, my recommendation would be that the forecast, conditional, I don't know whether this is correct, conditional forecast, should be constructed in terms of a probabilistic forecast. Then, as a final word, Wolfgang. We've been knowing each other since 1985, I believe, 31 years already. In many occasions we have agreed, sometimes we disagree. But as a small gift for your birthday, the following statement: I'm very glad for the disagreement that we had, because it sharpened my thinking as a scientist. Happy birthday, Wolfgang.